Hi, we're the thermoelectric generators for marine application Capstone team, comprised of Natalie, Julia, Zach, Brendan, and myself. Internal combustion engines produce a significant amount of hot gas exhaust that is wasted and released into the environment. In marine vessels in particular, there's a vast temperature gradient between the hot gases and the cold seawater, which provide ideal conditions for thermoelectric generators or TEGs. In a nutshell, TEGs are composed of semiconductors with added impurities that are able to produce the voltage potential when exposed to a temperature gradient. Previous contributions to this project include testing on an array of 3 modules and a hexagonal housing for 24. Both setups were unable to reach expected theoretical values because of parameters we'll discuss later. To understand the problem and identify key parameters, we decided to scale down to a single TEG sandwich and attempt to replicate the manufacturer's specs, to determine if this technology is feasible for energy recovery on marine applications.
A major area of improvement was the TEG module used. The previous prototype used a module capable of producing 14 watts of power, where we're testing modules capable of producing 20 and 22 watts respectively. Heating was also an area of improvement because the initial prototype struggled to produce enough heat for the ideal temperature gradient. So as the model is scaled up, larger and more powerful heat sources need to be used. Additionally, to improve the cooling block, different flow rates were used with the same cooling channel to optimize the cooling effects and get the desired temperature gradient for maximizing power output.
The fourth area we looked to improve was the insulation. Putting insulation in the sandwich would help stop heat from flowing around the TEG module and jumping straight from the hot plate to the cold plate. We also implemented a thermal paste to increase contact of the TEG surface to the hot and cold sides. The fifth area of improvement was making sure that the modules were under proper compression of 200 psi listed on the module spec sheets. The value to torque the bolts can be found theoretically, but it is also important to test how increasing compression can lead to increased power output. Previous studies have found increasing compression to be an important factor in achieving optimal power output. Our final single sandwich design has a TEG module sandwiched between a cooling block and a hot side plate, held together by 4 compression bolts. Cold water flows through the S-shaped path in the cooling block to keep the cold side of the TEG close to the ideal temperature listed on the spec sheet.
The testing setup for the single TEG sandwich includes a pump to pump cold water through the cooling block and a heating plate as the heat source. While the test is running, the hot temperature, cold temperature, and voltage are continuously recorded using LabVIEW. The output voltage recorded includes both the load and open circuit voltage because both are needed for the power calculations. During each test, the different parameters were altered individually to find the best conditions for maximum power output.
Although the hot plate in our test setup lists a maximum value of 540 degrees Celsius, we noticed that our hot side temperature plateaus around 210 degrees Celsius. The maximum hot side temperature reached was 233 degrees Celsius, which was just slightly lower than the High-Z module's ideal hot side temperature of 250 degrees. The cold side temperature fluctuated throughout our testing, but mainly stayed in the range of 30 to 40 degrees Celsius, also slightly lower than the High-Z module's ideal cold side temperature of 50 degrees Celsius. This fluctuation in the data can be attributed to the inconsistency of the tap water temperature. From our open circuit voltage data, we determined that the insulation has little impact on the open circuit voltage, and consequently is not worth applying. Adding Belleville springs to our bolts provided an increase in voltage, and a higher compression on our TEG modules also produced a higher voltage. Overall, our maximum voltage output was 8.01 volts. Out of all the parameters we tested, compression had the greatest impact on our power output. With the results from our single TEG testing, the analysis can be expanded to a 4 TEG sandwich to observe the effects of having multiple TEGs on the power output. Once the setup is optimized, the sandwich can be implemented into the overall hex design, and the final power output of the system can be determined.